beautiful state of Washington is the Grand Coulee Dam, which is a huge federally built dam on the Columbia River. And I nearly had an opportunity to visit Grand Coulee Dam and have a tour of the whole thing, except my 9-year-old daughter was tired and didn't want to go. So I missed out on Grand Coulee Dam. But I hope you don't miss out on Grand Coulee Dam, and I just want to tell you a little bit about it. It is way larger than even Hoover Dam, and it is a big energy producer, and it provides water to eastern Washington and Idaho and that whole region in the northwestern US. And so let's talk a little bit about how much energy is produced and also how much water is flowing. And so what we're going to do is we're going to talk about the size of the dam and how much energy it has the capacity to produce. And from that, we're going to do some calculations and estimate how much water actually flows through Grand Coulee Dam. How large is the Columbia River up there? And what we'll see is that the Columbia has earned its position in American lore and Woody Guthrie songs. It's a huge river up in the northwestern United States. So let's start with how much energy is produced and the capacity of Grand Coulee Dam. The power generation capacity is 6,809 megawatts. And recall that a nuclear power plant is about 1,000 megawatts. And so the capacity of this one dam to produce power is the equivalent of roughly 7 nuclear power plants. And another thing is, how high is the face of that dam? That dam is 550 feet high. So, believe it or not, this is all we need to do the mathematics to tell us how much water is flowing through that dam. We have to make some assumptions, but this is all we need. And so let's make the assumptions and do the math and see how close we can get. So the first thing we'll do is we will change 550 feet to meters, because that's something, as we'll see, we're going to need to change this one at least to metric, and then we'll be just fine going forward. So let's just do it right here. 550 feet times 1 meter per roughly 3.3 feet. And that gets us 168 meters. So that's now the height of the dam in meters. And now let's go and remember our basic formula. It's that energy equals mass times gravity times the amount of how far it's falling. And so this is the energy that is imparted to water, and it's based on how heavy, what the mass of that water is that's falling, and the gravitational constant. And as long as we're on Earth, this isn't going to change. And then how far is that water falling? Because the further it falls, the faster it falls, and the more energy is imparted to it. And so, luckily, we can just, we know immediately that this is 9.8 meters per second squared. And the height we also measure in meters, and the mass we measure in kilograms. And so what we're going to do, eventually what we want, our goal, here we'll put it right up here. Our goal is CFS, cubic feet per second, passing through Grand Coulee Dam. And so we're going to get that from here. So we're lucky in one sense. Megawatts is already measured per second. And so the mass we want will also be measured per second, because megawatts is a flow of energy. And so this is going to be a flow of water passing through. And so what I'm going to do over here is I'm going to restate this using the actual unit conversions. So a megawatt is a kilogram meters squared per seconds cubed, and that equals the mass, which is kilograms per second. So that's flowing water measured by its weight, times meters per second squared, times the height in meters. And so these are the units, and as you can see, they're all here. Kilogram, kilogram, meters squared, meters times meters, seconds cubed, seconds times seconds squared. So what we're going to do now is we're going to substitute in everything we have here. Oh, and there's one more thing we'll assume. Remember that hydropower plants are only about 90% efficient. And so we will multiply all of this by about 0.9, because there's going to be a little less energy produced given what's the height of the dam and the power and the amount of weight of the water and so forth. So now what we can say, this E is the same here. So 6,809, well, let's just do it this way. Kilograms meters squared per seconds cubed equals some amount of kilograms per second. We don't know how much, so we'll just say X kilograms per second times 9.8 meters per second squared, the gravitational constant, times 168 meters. And now we're going to multiply all of that by 0.9, because that's our efficiency factor. Not all of this is going to be translated into energy. There's going to be a little bit lost, and so we're going to just shrink all of this by multiplying it by 0.9. Okay, so we have to isolate this x that we don't know by itself, and so the way we'll do that is we will take all of this and we'll divide both sides by it, and so all of these will just cancel away to 1, and we'll get this by itself, and we'll have all of our solvable math units over here. So I think what I'll do is shift over to this part of the whiteboard, and we'll say 6,809 kilograms meters squared per seconds cubed divided by, now we'll just put all of these in, 9.8 meters per second squared times 168 meters times 0.9, and all of that is going to equal something kilograms per second. And so when we do this big math problem, we get all kinds of units canceling left and right, and we come up with well, let's see if I have so what we get of all of this is that x equals 4.6 million kilograms per second. So just by doing all that math, we get 4.6 million kilograms per second. So please check that yourselves. Let me make that a capital M as it should be. And so now the last thing we need to do is change kilograms to cubic feet. And we can do that in a fairly straightforward way. First thing we'll do is we'll say 4.6 kilograms per second times how many pounds per kilogram? Well, it's 2.2 pounds per kilogram. And then the next thing we have to do is just change pounds into cubic feet. And so we'll put 1 cubic foot in the numerator, and a cubic foot actually weighs more than you think. It weighs 62.4 pounds. And then when you do that math, what you end up with, oh, I left out a million. When you do that, what you get is 162,000 cubic feet per second. And 162,000 cubic feet per second is a huge flow of water. And it's not all of the water that flows in the Columbia River. The Columbia River, on average, has about 265,000 CFS flowing in it. And so this represents only about 60% of all the water that flows in the Columbia River. Only about 60%. And that makes sense because you're not capturing all of the water behind a dam, and you're not putting all of the water in a river through the turbines and the generators. And so, so what we've seen here is that a huge amount of water of the Columbia River is flowing through Grand Coulee Dam, but not all of it.